Hello, my name is Kavindu, and today I'll be presenting on open source hardware for multiprocessor system on chips, or often known as SoCs, with a focus on profiling OpenPiton. Open source hardware means that the design of the processor, for example, the Verilog or RTL code, is freely available under open licenses. This allows researchers, students, and companies to customize, study, and improve the designs without any restrictions. In the context of multiprocessor SoCs, we are talking about integrating many CPU cores on a single chip to run parallel tasks efficiently. With open source hardware, this design process becomes more collaborative and transparent. Open source SoCs are important because they lower barriers to innovation. Historically, we saw early projects like OpenRISC in the 2000s and later the RISC-V movement in the 2010s, which made open source hardware much more mainstream. The benefits include lower development costs, the ability to rapidly prototype ideas, and the possibility to audit hardware for security. However, challenges remain. For example, verifying complex hardware is very difficult, and actually manufacturing silicon chips is expensive. OpenPiton is one of the most significant projects in this space. It was launched in 2015 by Princeton University, and it started out as an extension of the OpenSpark T1 design. Over time, it has expanded to support RISC-V cores as well. The main goal of OpenPiton is to provide a scalable platform for many core research, essentially a framework where researchers can study systems that scale from a few cores to potentially millions. The architecture of OpenPiton is tile-based. Each tile contains a processor core, private L1 caches, and a router. These tiles connect together using a network on chip or NOC, which allows communication across the chip. A key feature is cache coherence, making sure all cores see a consistent view of memory. On FPGAs, OpenPiton has been scaled up to more than 25 cores, but the design is theoretically capable of millions of cores in a research context. OpenPiton is not just a theory. It comes with tools for simulation like Verilator and even ASIC design support, meaning it can be fabricated into real silicon. In recent years, the project has added RISC-V integration thanks to collaboration with its Zurich, which makes it even more relevant today. The project also has an active community on GitHub with over 1,000 stars, showing real global interest. OpenPiton has already been used in research areas such as studying cache security and designing prototype chips. Its influence can be seen in other projects like Google's OpenPiton, which is now a widely recognized open source silicon project. Looking forward, frameworks like OpenPiton can play a key role in AI accelerators, edge computing devices, and secure hardware designs where flexible, transparent hardware platforms are critical.
Think your phone's fast? It's got a team of processors working overtime. These tiny powerhouses combine multiple processors, think CPUs, GPUs, and more, onto a single chip. That means smoother gaming, lightning-fast browsing, and smarter apps, all without draining your battery. From smartphones to smart cars, multiprocessor SoCs are the brains behind today's tech, making everything faster, smarter, and cooler. Next time your device feels magic, remember, it's a team effort under the hood.
To conclude, OpenPiton democratizes access to multi-core research. It provides a flexible and scalable platform for both education and innovation. For those interested, more resources are available at openpiton.org and the GitHub repository. Thank you very much for listening. This brings me to the end of the video. Thank you for your attention.